Welcome to G Fun Facts Online. Let's talk about a paradox. What if I told you one of the greatest inventions of the 20th century, a process that feeds nearly half the world's population, is also one of our biggest environmental villains? We're talking about the chemical process that creates modern fertilizer. For 100 years, it has saved billions from starvation. But it's done so by burning colossal amounts of fossil fuels, polluting our water, and warming our planet. Today, we're exploring the dawn of a new agricultural age, a suite of groundbreaking technologies known as green nitrogen fixation that promise to power a greener revolution. We're moving from the carbon-intensive gray of the past to the vibrant green of the future. To understand the revolution, you have to understand the titan it's trying to replace, the Haber-Bosch process. Invented in the early 1900s, it was a scientific miracle. Our atmosphere is nearly 80% nitrogen, but it's locked up by an incredibly strong triple bond that plants can't use. Haber-Bosch was the first industrial process to crack that code. In simple terms, it takes hydrogen, usually stripped from natural gas in a very CO2-intensive step, and combines it with nitrogen pulled from the air. Under immense pressure and searing heat, around 450 degrees Celsius, it forces them together to create ammonia, the building block of nitrogen fertilizer. This invention allowed us to grow food on an unprecedented scale, enabling the global population to explode from 1.6 to nearly 8 billion people. Without it, our world would look vastly different. But this miracle has a dark side. The process is unbelievably hungry for energy, consuming between 1 and 2% of the world's entire annual energy supply, mostly from fossil fuels. It's a massive source of CO2, responsible for over 1% of all human-made carbon emissions. And it doesn't stop there. When this fertilizer is applied to fields, it releases nitrous oxide, or N2O, a greenhouse gas nearly 300 times more potent than CO2. It's now the single biggest human-made threat to the ozone layer. And there's more. Often, more than half the fertilizer we apply to fields isn't even used by the crops. It just runs off into rivers and oceans, triggering what's called eutrophication. This flood of nutrients causes huge algal blooms that block sunlight and suck all the oxygen out of the water when they die, creating massive aquatic dead zones, like the one that forms each year in the Gulf of Mexico, killing off entire ecosystems. That excess nitrate also seeps into our groundwater, contaminating drinking water and posing serious health risks. The Haber-Bosch process saved us from famine, but it locked our food system into a destructive dependency on fossil fuels. The need for a new way isn't just a preference, it's a necessity. But what if I told you nature had already perfected this process, billions of years before we ever did? This is the promise of biological nitrogen fixation, or BNF. The stars of this show are tiny microbes called diazotrophs. These bacteria possess a molecular machine, an enzyme called nitrogenase, which is the only known biological tool capable of breaking that stubborn nitrogen triple bond and turning it into usable ammonia for plants. The most famous example is the symbiotic relationship between rhizobium bacteria and legumes, like soybeans, peas, and peanuts. The bacteria infect the plant's roots, which form special nodules to house them. Protected from oxygen inside these nodules, the bacteria get a steady supply of energy from the plant, and in return, they provide a direct, constant stream of fertilizer. Farmers have used this wisdom for centuries, through crop rotation, planting nitrogen-demanding corn one year and nitrogen-fixing soybeans the next to naturally replenish the soil. Today, science is taking this to a new level. We have biofertilizers, which are essentially cocktails of these high-performing microbes that farmers can add to their seeds or soil. But the real frontier is genetic engineering. Scientists are using CRISPR to design supermicrobes that are more efficient and resilient. And the holy grail of this research is to engineer our staple crops, like wheat, corn, and rice, to fix their own nitrogen. It's a massive challenge, like teaching a cat to bark, but imagine a world where the world's biggest crops could fertilize themselves. A recent stunning discovery of a microbe that has become a permanent nitrogen-fixing organelle inside an algae cell, a so-called nitroplast, shows us that nature has already created a blueprint for how this might be possible. While some scientists are looking to biology, others are turning to pure energy, aiming to power fertilizer production with renewables. This is the electric revolution. The leading approach is to re-engineer the Haber-Bosch process. Instead of getting hydrogen from natural gas, we can use renewable electricity from solar or wind to split water into hydrogen and oxygen. This green hydrogen is then fed into a smaller, cleaner ammonia synthesis loop. The biggest advantage here is decentralization. Instead of a few gigantic, polluting chemical plants, you could have modular, scalable units. Imagine a farming co-op in a remote region with its own solar-powered ammonia reactor, producing fertilizer as needed from just air, water, and sunlight. It would slash transportation costs and empower local communities. This green ammonia can also act as a way to store renewable energy, a liquid fuel for when the sun isn't shining or the wind isn't blowing. The main hurdles right now are cost and efficiency, but as renewable energy gets cheaper and cheaper, this technology becomes more and more viable. An even more futuristic concept is photochemical fixation. This is about using the energy of sunlight directly to power the reaction on the surface of a special material called a photocatalyst. The vision is beautiful, a device that uses only sunlight, air, and water to produce ammonia. It's like artificial photosynthesis for fertilizer. This tech is still in its early days, with very low efficiency, but the potential for a completely direct, solar-powered system is a powerful driver of research. The innovation doesn't stop there. The future of fertilizer is starting to look like something from a science fiction novel. Take plasma-assisted nitrogen fixation. This is essentially bottled lightning. By using electricity, ideally from renewables, to create a plasma, an ionized gas, we can create a highly energetic environment that easily rips apart nitrogen molecules in the air. These reactive nitrogen atoms can then be used to create liquid nitrogen fertilizer. The process is instant, it can be turned on and off at will, and it's perfectly suited for on-demand production right on the farm. Then there's nanotechnology, which is bringing us smart fertilizers. Instead of dumping a large amount of fertilizer on a field at once, nanotechnology allows us to encapsulate nutrients inside tiny coatings. These coatings act as a barrier, releasing the fertilizer slowly and gradually, perfectly synchronized with the plant's needs over weeks or even months. It's like spoon-feeding the plant instead of force-feeding it. This drastically improves efficiency, meaning less fertilizer is needed, which in turn means far less pollution and runoff. Finally, the last piece of the puzzle isn't about how we make fertilizer, but how we use it. This is precision agriculture. It's a data-driven approach using a suite of digital tools. Networks of IoT sensors in the fields monitor soil moisture and nutrient levels in real time. Drones and satellites provide a bird's-eye view. All this data is fed into an AI platform, which acts as the brain of the farm. Its algorithms analyze everything to predict the exact nutrient needs for different parts of a field. That information is then sent to GPS-guided tractors that apply exactly the right amount of fertilizer in the right place at the right time. This move away from one-size-fits-all application to hyper-targeted nutrition dramatically reduces waste, saves farmers money, and protects the environment. So what does the path forward look like? The transition away from our century-old fossil fuel-based system is a massive undertaking. The biggest hurdle for all these new technologies is cost. Haber-Bosch has had a 100-year head start in optimization, but the economic landscape is shifting rapidly. The cost of solar and wind energy has plummeted, making the key ingredient for green ammonia cheaper every year. At the same time, policies like carbon taxes are starting to account for the true environmental cost of the old process, leveling the playing field for greener alternatives. The future won't be a single silver bullet. It will be an integrated system where all these solutions work together. Imagine large-scale solar ammonia plants in sunny deserts, decentralized plasma units powering remote farms, and major crops engineered to make some of their own nitrogen. And imagine every single farm, large or small, using AI and precision technology to ensure that every single drop of that precious fertilizer is used to its absolute maximum potential. We are at the dawn of a profound shift in how we feed ourselves. It's more than just new chemistry. It's a rethinking of our entire relationship with the planet's natural cycles. It is a revolution that promises to finally feed the world without costing the Earth. Thanks for tuning in to G Fun Facts Online.